Hi again. This video covers the fundamentals of calibrating count distributions to insurance count data. Now, first of all, various paradigms have been proposed for calibration, like the maximum likelihood estimation framework, the method of moments, and Bayesian statistics. In this course, you will focus exclusively on the framework of maximum likelihood estimation, popularized by Sir Ronald Fisher in the 19th and 20th century. Now, the likelihood function is the density of the observed data, with the parameters taken as variable and the data as fixed. So let n1 up to nn be independent and identically distributed random variables with a common count distribution p that depends on some unknown parameters psi. The likelihood of observing outcomes k1 up to kn for those random variables is then given by their joint density. Now, since these variables are independent, that is simply the product of the probability function of each random variable ni evaluated in the registered or the observed outcome ki. And you will approach this resulting likelihood function as a function of psi. And you're going to search for those parameter values psi hat that maximize this function. Now, to find MLEs, to find maximum likelihood estimates, you typically switch to the log likelihood, denoted here with capital L. And you take the derivative of L with respect to each of the unknown parameters in the vector psi. And we call those derivatives the Fisher score. We put them together in the Fisher score vector U. Set this score to 0 and solve the system of equations to find the MLEs, right? Now, let's do this explicitly for the Poisson and for the negative binomial distribution. We consider data in the following format. So each policyholder I is followed during a period of exposure of length di. And during this period of exposure, the policyholder produced or reported ki claims. Now, assume the annual number of claims reported by the policyholder is Poisson distributed with mean lambda. Then the question is, what is a good value for this lambda? So you're gonna write down the log likelihood as a function of lambda. And here too you replace the probability function of the Poisson with parameter lambda times the exposure of the policyholder with the expression as discussed earlier in the course. You rearrange this expression and you're gonna ignore all terms that do not depend on lambda, since what you want to do is you want to optimize this function with respect to the unknown parameter lambda. So here's what you get, and you're going to take the first order derivative of the log likelihood with respect to lambda. You're going to put this score function equal to 0 and solve for lambda. That would give you the expression for the maximum likelihood estimate of lambda for this particular given dataset. Now, the MLE as obtained over here has a very intuitive expression. You see that you estimate the lambda parameter as the annual mean claim frequency. That is, it is the ratio of the number of observed claims, that's the sum over all observed claims ki, sum over all policyholders I, divided by the sum of the total exposure in the dataset. That is the sum of all the DIs. And as such, the MLE captures the average number of claims reported per unit of exposure in the portfolio. And that's a very intuitive meaning for this maximum likelihood estimate of lambda in the setting of a Poisson distribution. Now, things become a bit more complicated when you work with the negative binomial distribution. So again, you're going to write down the log likelihood starting from the probability function of the negative binomial. Now you see that two parameters matter. There's a parameter a and a parameter lambda. So you want to optimize this log likelihood function over the unknown parameters a and lambda. So you take the derivative of the log likelihood with respect to a on the one hand and with respect to lambda on the other hand. You put these expressions equal to 0 and solve them. However, that's not going to work analytically, and you will have to rely on a numerical technique to solve this set of equations. A statistical software package like R that will be used in this course will do this for you under the hood. Now, as you know from a statistics course, maximum likelihood estimators enjoy a number of convenient properties. In general, these properties are asymptotic, so that means that they rely on large data sets. But since non-live actuaries typically use large data sets, they generally trust in the large sample properties of their maximum likelihood estimators. Just to sum up, the useful properties here are consistency, invariance, and asymptotic normality. The general idea that underlies statistical inference is the comparison of particular statistics from an observational data set, like the mean, the standard deviation, with an appropriate reference distribution in order to judge the significance of those statistics. Now, in order to make statistical inference, to do statistical inference about the parameters of a count model or a risk model, you will first have to be able to express the uncertainty about certain parameter values that you obtained. And you will do this by estimating the variance-covariance matrix of the vector with the maximum likelihood estimators. And this matrix gives us on the diagonal the variance of the maximum likelihood estimator of each of the parameters in the model, and the off-diagonal elements give you the covariance between the maximum likelihood estimators of two parameters xi I and xi j. Now, in order to work with, for example, the asymptotic normal distribution of the MLE of a parameter vector xi, or in order to set up a hypothesis test, you will need this asymptotic variance-covariance matrix, and you will estimate it as the inverse of the Fisher information matrix, denoted here with calligraphic I. Now, a convenient way to obtain an estimate of this matrix is by using the following property. So the Fisher information matrix, you can obtain it as minus the expected value of the matrix with the second order derivatives of the log likelihood, and that holds under certain regularity conditions. And this latter matrix, so the matrix with the second order derivatives of the log likelihood, we also call that the Hessian matrix. Now, because this type of calculations may look pretty obscure, the next three sheets, so that's 42, 43, and 44, include a detailed and worked out example. So I invite you to verify the calculations on these sheets, which concern the estimation of parameters mu and sigma in a log normal distribution. And finally, you will retrieve the asymptotic variance-covariance matrix of the maximum likelihood estimators of the parameters mu and sigma in this distribution. So that's an exercise for you to verify all these derivatives and calculations. Now, as explained, so as discussed in the example with the negative binomial distribution, calculation of the maximum likelihood estimates often requires iterative procedures like Newton-Raphson or Fisher scoring. In these numerical recipes, you will use the Hessian, that's the matrix with the second order derivatives of your likelihood. You will also use the Fisher score vector, that's the vector u with the vector with the first order derivatives of your log likelihood with respect to the unknown parameters. Now, what you essentially want to do is you want to find the xi hat vector such that u, the set of first order derivatives evaluated in this xi hat, is 0. That is, the vector with the first order derivatives evaluated in xi hat should be 0. Now, to solve this numerically, you can write down a first order Taylor expansion of u around xi hat. And then with xi star close enough to xi hat, you will find the following expression. So this is a first order Taylor expansion. Now you can use this relation to find the xi hat for which the vector of first order derivatives will approximately be equal to 0. So you're going to isolate, you're going to solve, and you're going to isolate xi hat from the above expression. And that leads us to the essential operation in a Newton-Raphson strategy, or in Newton's method, to find successively better approximations to the roots, or the zeros, of a zero-valued function. In this case, the first order derivatives of the log likelihood. So under the hood, this is exactly what a statistical package like R will do when calculating the MLE of the parameters of a count distribution, when that is not analytically possible to do so. Now, an alternative procedure to calculate numerically the MLEs of unknown parameters will use the connection between the Fisher information matrix and the Hessian informatics, and that relation is repeated over here. This is the so-called Fisher scoring algorithm. It's a form of the Newton's method that is used in statistics to solve maximum likelihood equations numerically. Now, having this as a background to calculate maximum likelihood estimates and estimators, we're going to continue with some considerations regarding hypothesis testing. So the asymptotic normality of the MLE then leads us to the following distributional result, where the hat xi j is the maximum likelihood estimator of the unknown parameter xi j, and xi j is the true value of this parameter. Sigma hat xi j is the standard deviation of the maximum likelihood estimator xi j hat. Now you can find it as the square root of the j diagonal element of the variance-covariance matrix of your MLEs. Now in practice, this standard deviation of the xi j hat often involves unknown parameters, such that it is estimated by the inverse of the Fisher information matrix, where the unknown parameters xi are replaced by their estimates. The asymptotic distribution then becomes a student t distribution with n-1 degrees of freedom, where n is the number of observations in your sample. And you recognize these distributional results as the tools you will need to formulate a hypothesis test with respect to the value of one particular parameter xi j from your distributional model. We'll come back to that later on. You can also take this whole thing one step further and formulate a hypothesis test for the vector of parameters xi, instead of putting focus on a single entry from this vector as we did in the previous sheet. Now, the Wald test statistic allows you to test a null hypothesis where xi equals xi0 versus the alternative where xi differs from xi0. And this test statistic is approximately chi-square distributed under the null hypothesis, the degrees of freedom in this chi-square distribution being equal to the dimension of the parameter vector xi. The test statistic here measures the distance between the maximum likelihood estimate xi hat and its hypothesis value xi0. The null hypothesis will be rejected if the observed value of this statistic is too large, that is, if the maximum likelihood estimator is too far from xi0. A useful type of test to keep in mind during this course is the likelihood ratio test. And this test allows you to compare nested models. So say that the model under the null is a constrained model with j parameters less than the full model under the alternative. Typically, in the null, you would put j parameters equal to 0 to investigate their significance. Then let xi tilde be the maximum likelihood estimator under the null hypothesis, and xi hat denote the maximum likelihood estimator under the alternative. The likelihood ratio test then uses the ratio of the likelihood of the full model and the likelihood of your restricted or reduced nested model. This likelihood ratio test statistic then equals 2 times the log of this ratio. There is evidence against the null hypothesis when the observed value of this test statistic is large. Indeed, a large ratio would imply that the likelihood obtained under the null model is way larger than the likelihood under the restricted model. Put otherwise, if both likelihoods are approximately equal, the ratio would be would almost be equal to 1, and the logarithm would become 0. And in that situation, the likelihood ratio test statistic takes a small value. There is no evidence to prefer the full model over the restricted one. So under the null hypothesis, and with the sample size large enough, the test statistic follows a chi-square distribution with j degrees of freedom, where j is the difference in the number of parameters used by the full and the restricted model. The chi-square approximation to this distribution of the likelihood ratio testing is valid only under certain regularity conditions, right? You can read more about that over here. Now, the chi-square approximation to the distribution of your likelihood ratio statistic is valid only when considering nested hypotheses. So with non-nested models, we cannot make use of this test for model comparison. But another useful tool to compare different models calibrated on the same data are information criteria like the Akaikis information criterion or the Bayesian information criterion. Both criteria combine -2 times the maximum log likelihood obtained with a penalty that is a function of the number of parameters and the sample size n. Hence, those criteria evaluated trade-off between goodness of fit, as captured with the log likelihood of your model, and complexity of your model, as captured with this penalty. When comparing models with these criteria, you will prefer models that result in smaller values. Given a set of candidate models for the data, the preferred model would thus be the one with the minimum value for AIC or BIC. So that's it for this video. So the sheets end with an overview of the probability models that we discussed, the Poisson, the negative binomial, the zero inflated Poisson, some useful expressions over here that you can verify. And I also list a set of learning outcomes that you should be able to master at this point.